G'day, in the previous two videos we've been looking at how we apply the motor effect and induction to motors and generators. Today we're going to be looking at some further applications. So today we're covering dot point 6, point 4, point 2 and 3, finishing off inquiry question 4, looking at what happens to stationary and moving charged particles when they interact with electric and magnetic fields. Particularly, we're looking at the operation of AC induction motors. Today we've already looked at AC and DC generators. But also we're going to be relating Lenz's law to this concept of magnetic braking, which is not a motor or generator, but still an application of the motor effect and induction. So our two key learning intentions today. First off, explain how the motor effect and induction are applied to an AC induction motor. And then very similarly, we'll look at magnetic brakes. So first off, an AC induction motor comes with two very clear and key sections. We have the stator, which is supplying a magnetic field to the rotor, which is the section of the motor which is actually rotating. The stator inherently then is stationary. Generally in the rotor, you have some sort of what we call squirrel cage, which is a cylinder with very defined separate sections of conductive material. This material can experience induced current from magnetic fields which are generated by the stator. And because each of these sections of conductors then produce an induced current, that induced current can then interact with the magnetic field around it, causing a Lorentz force, a force generated by the motor effect. And we're set up in a way that that force experience, because we're sitting on an axle, causes rotation on the rotor. In order for an induction motor like this to work, generally speaking, we need to use AC voltage, meaning that the direction of the current that's running through the coils at the stator are oscillating, meaning that the magnetic fields which are generated at the stator are also oscillating. And because there is an oscillation of flux, there is a change in flux. The change in flux leads to induction in the conductors on the squirrel cage. And as we said before, that induction will lead to a current running through each of the parts of the squirrel cage, which can then interact with the magnetic field, which is again being generated by the stator, which in turn generates torque. A lot of the time, AC induction motors have sections of coils which are opposite to each other, just like we can see in this diagram here. We've got pair A, pair B, and pair C. And these pairs of coils on the stator always run magnetic field from north to south. However, they're generally set up in ways in which each pair of coils will take their turns in having the largest magnetic field at one given time. As such, you get areas within this round stator where there is a very clear magnetic north and a very strong magnetic south. However, because you are going through these periods of high and low magnetic field or high and low flux, and because this increase and decrease is not what we say in phase for each of the coil pairs, what ends up happening is over time, the strongest north field moves around the stator. In other words, with one oscillation of magnetic field, the direction of magnetic north does one full rotation. Generally, AC runs on 50 Hertz. What this means is that the magnetic field generated by the stator rotates 50 times every second. So not only is this rotating magnetic field leading to a change in flux which induces current into the rotor, but it also rotates in such a way that this causes the rotor to follow this magnetic field, in other words, causing rotation and torque. Another application of induction is magnetic braking. We've seen many times before that if a magnetic field changes around a conducting material, then an EMF is generated. This comes back to Faraday's law. But more than that, through Lenz's law, which builds on the law of conservation of energy and Faraday's law, we see that there is always a very clear defined direction for which the induced current must flow. In this scenario, we see that the current needs to move around the conductor in this direction. In doing so, by the right-hand grip rule, we will generate a magnetic field which runs through the center of the conductor, which opposes the incoming magnetic field. Again, this is an application of Lenz's law and the conservation of energy, which ensures that the generated magnetic field opposes the direction of motion of the magnet, opposing the change in flux. I'm sure that we can appreciate in this scenario that this upward magnetic field is going to put a force on the magnet if it were to be, say, dropped, which would resist motion. As such, it acts as a resisting force, slowing down the magnet as it moves through the tube. This resistive force can be harnessed under certain applications to essentially act as a brake and slow a moving object down through the application of these electromagnetic concepts such as induction and Lenz's law. What is shown here is a very simple model of a magnetic brake. Essentially, you have a magnet on either side of a rotating disc. Let's say that this is a wheel. And as the disc rotates around the magnetic field, there is going to be this process of induction and an application of Lenz's law, which produces a resisting force, which is going to resist the rotation on the wheel. That is shown in this diagram here. Essentially, if the wheel rotates around and around and around, and there is a magnetic field which goes through part of it, eddy currents are going to be produced. And they rotate in different ways depending on whether the part of the wheel is exiting or entering the magnetic field. In both cases, the eddy currents need to rotate in a way which generates a force on the disc which opposes motion. In other words, the force needs to go back in this direction so that there is a force applied which goes in the anti-clockwise direction. By using our right-hand rule for the motor effect, if we place our magnetic field vector down, our force vector to the right, we'll see that our current vector goes into the page, which is exactly what is being represented here in this diagram. We have a downward magnetic field. We know that our force needs to tend towards the right, leading to a resistive force in the anti-clockwise direction. So therefore, the current which is moving in the disc around where this magnetic field is going to go effectively into the page. As a result, we have eddy currents which rotate around clockwise on this right-hand side and anti-clockwise on the right-hand side. And again, both of these sets of eddy currents will generate a force which runs opposite to the direction of motion. So then as the disc rotates, there will be a resisting force apart from friction, which is being applied to the disc, causing it to slow down. So some advantages of using induction-based devices. There are generally two. First off, reduced friction means reduced maintenance. So let's imagine that we're talking about a motor in particular that runs on commutators and brushes, for example. The contact between the commutator and the brush will cause friction, and that will cause wear on both of those pieces of equipment, essentially meaning that the durability of those parts are low and requires maintenance, repair, and replacement in a lot of cases. While conceptually induction devices can be a little bit more involved, they are actually usually quite easy to build and are low cost. So that is another advantage for them as well. This brings us to the end of Module 6. We've brought together lots of concepts around the interaction between charged particles and magnetic fields and vice versa. And hopefully we can begin to appreciate just how important the field of electromagnetism has been to the development of technologies that dictate our everyday lives. In future videos, we'll move on to Module 7, which is all about light, a further application of electromagnetism. But until then, have a good one.